Hello, welcome to a video about diffraction gratings. We've got an image here of a beam of light being diffracted through one of these diffraction gratings. So I'll start with the learning intentions for this section. The interference pattern produced by light passing through a transmission diffraction grating demonstrates the wave behaviour of light. Transmission diffraction gratings can be used to analyse the spectra of various light sources, and the formula d sine theta equals m lambda can be used to analyse the interference pattern. There's a fair few success criteria for this video, so I'll quickly whiz through them all and then we'll go through the content. So in stage 2 physics, you need to be able to describe how diffraction by the very thin slits in a diffraction grating allows the light from slits to overlap and hence interfere to produce significant intensity maxima at large angles. You also need to be able to derive d sine theta equals m lambda for the intensity maxima in the pattern produced by a transmission diffraction grating, where d is the distance between the slits in the grating, theta is the angular position of the mth maximum, and m specifies the order of the maximum. So is it the first order, second order, third order, so on and so forth. You also need to be able to solve problems using this formula, and you need to be able to sketch a graph of the intensity distribution of the maxima produced by a grating for monochromatic light. So monochromatic light is light of the same wavelength. You need to determine from the distance between the slits in the grating the maximum number of orders possible for a given grating and wavelength. You also need to be able to describe how a grating can be used to experimentally determine the wavelength of light from a monochromatic source, and you need to be able to describe and explain the white light pattern produced by a grating and identify the properties of a grating that make it useful in spectroscopy. So a decent amount of things we have to be able to do, but hopefully this video will help us with that. So what is a transmission diffraction grating? So it's an opaque screen with a large number of closely spaced parallel gaps or slits. So if we think about Young's double slit experiment, it's kind of like that on steroids. So a diffraction grating just has loads more than just two slits, and they're all equidistant apart. The slits may be called lines or rulings and are cut with a diamond or with a laser. All slits have the same width, and as I said, they're the same distance apart, so the spacing between the centres is the same for every single slit. Waves diffract and interfere as they move away from the slit. So in our diagram here, light is modelled as a ray. So we've got a parallel beam of monochromatic light or a laser light that has shone through this grating, and in this image here it looks like this single beam has become 5 different beams. What is actually happening is, if you imagine looking at this from a bird's eye view, then light will be propagating through each of these gaps. Each of these gaps is a gap in the diffraction grating, and the light will be diffracting, so the waves will be spreading out, and at certain points waves from 2 different slits will meet, and at some points they might both be like the trough or the peak of the wave might be in the same direction, so the waves will superimpose or interfere constructively. At other points you'll get a crest of one wave meeting with a trough of another wave, and when they superimpose, so when they interfere, they'll interfere destructively and cancel each other out. So what ends up happening is that you get on the screen bright bands and dark bands, and they correspond with constructive and destructive interference that has occurred. So it can look a bit like one beam of light that has been then divided into 5 beams of light, or whatever many beams of light, after passing through a diffraction grating. So for deriving the diffraction grating or optical path difference formula, which is this formula here, we'll start off by remembering that the incident light is coherent after it's either passed through a single slit or if it's a laser, and therefore the light waves arrive simultaneously at each slit of the diffraction grating or each of the double slits in Young's experiment. So they're therefore in phase. So the crest of each wave from each different slit is happening at the same time as the crest of every other wave. After they pass through each slit, the light waves diffract, so they spread out and they bend, and they then interfere with each other. Now, if we consider a certain point on the screen over here where all of these light waves are travelling towards, for this particular point on the screen, say it's a maximum, so it's a bright fringe, we assume, even though it couldn't possibly be true, we assume that each of these paths is parallel. And the reason that we can assume that is because the distance here compared with the distance to the screen, which is L, that distance between each slit in the grating is so small, so we just end up assuming that the light waves, which are modelled as rays in this diagram here, we just end up assuming that they're parallel because, like, they pretty much are, but obviously they're not exactly parallel because that would be impossible. But that's the assumption that we have to make. Now, the path difference, so the difference between the distance that each wave travels from each slit, so here and here compared with the top wave, is equal to d multiplied by sine theta. Hopefully you can see if we have this diagram here where we've zoomed in and we've then looked at the right angled triangle that this produces, hopefully we can see that this length here, which is this length here, hopefully we can see that that is equal to the hypotenuse multiplied by sine theta because it's an opposite over hypotenuse situation. So we're working out what the opposite side is. The opposite side is delta r, so the difference between the lengths of parts of each light wave, and we're multiplying sine theta by the hypotenuse, which happens to be the distance between the midpoint of each slit in the grating. Now, if you think about your similar triangles, it also happens that the angle here is equal to the angle here. So the angular position of this maximum over here So the bright fringe on the screen happens to be the same angle as our original theta, and you can work that out by thinking about how there is 180 degrees in a triangle, then there's also 180 degrees in a straight line, and if you think about your triangle here, we've got theta, we've got a right angle here, and then we've got whatever other angle here. So if we now think about our straight line, we've got a theta here, this here is a right angle. Sorry, I'll start with the right angle here actually, and then we'll think about this other angle, which is also the other angle in the triangle. Then our angle here can only be equal to theta, because if we're minusing 90 degrees and this other angle from 180, then the space that we'll have left must only be equal to theta. So if you're wanting to find the path difference between two waves from adjacent slits, then you just have to multiply the length between the midpoint of the slit, so d, multiplied by sine of the angular position of whatever maxima or minima that you're considering. So if theta, or the angular position, is at a bright fringe, so where constructive interference is occurring, then the path difference between each wave, so the length difference between the path that each wave has travelled, must be equal to an integer number of wavelengths, so that the waves are perfectly in phase, even though they've travelled different distances. One of them has travelled one full wavelength further, so that peak can occur where a peak is occurring of the other wave, and a trough will occur where a trough is occurring on the other wave, so they're in phase. And therefore, because the path difference is the same between each successive wave, or the waves from each successive slit, at each fringe point, so at each constructive interference or maxima, however many waves from however many slits are in phase, and this results in positive interference or constructive interference. The particular order of maxima, and also refers to the number of wavelengths difference between each successive wavelength path from a diffraction grating, so from the slits in a diffraction grating. Looking at distance between slits, this is often stated as the number of lines, which is represented with a capital N per millimetre. So this is just the inverse of the distance between slits. If you want to work out what the distance is between the midpoint of each slit, and you're given this in lines per millimetre, then all you have to do is divide that millimetre, so 1 millimetre, by however many lines there are in that millimetre, and you'll get the distance between each slit. So for example, a transmission grating has 800 lines per millimetre. What is the distance between each slit? So to do this, we use our formula, D equals 1 on N, so D equals, we'll divide 1 by 800 by 10 to the 3, and the reason we're dividing by 10 to the 3 is because we're now doing per metre, because when we use D in our other formulas it needs to be in metres, so if there's 800 lines per 1 millimetre, then there's going to be 800 by 10 to the 3 lines per metre. if you pop this into your calculator, you'll end up with an answer of 1.25 by 10 to the negative 6 meters. So the distance between each slit is 1.25 by 10 to the negative 6 meters. So for an example, we've got violet light with a wavelength of 400 nanometers, and it illuminates a transmission grating with 300 lines per millimeter. What is the angular position of the second order of maxima on the screen? So now this is looking at our third success criteria here. So to do this, to solve problems involving the use of d sine theta equals m lambda, we can just write this out because we know that's what we have to use. And we can write out what we already know. We know that the wavelength is equal to 400 nanometers, which is 405 nanometers, which is 405 by 10 to the 9 meters. We know that d is going to be equal to 1 on n, which is equal to 1 on 300 by 10 to the 3 lines per meter, and that is equal to 3.3 by 10 to the negative 6 meters, and we know that m must be equal to 2 because we're looking for the second order of maxima on the screen. We're not sure what theta is, but that is what we are looking for. So I'll rearrange this formula now to make theta the subject. So theta is equal to inverse sine of m lambda on d. I'm going to continue this down here just where I've got more room. So theta is equal to inverse sine of m, which is 2, lambda, which is 405 by 10 to the negative 9, and then divided by d, which is 3.3 by 10 to the negative 6. Pop all of that into your calculator and you'll end up with an angle of 14.1 degrees. So the position, or the angular position, of the second order of maxima must be 14.1 degrees. So now we're looking at this success criteria here. So sketch a graph of the intensity distribution of the maxima produced by a grating for monochromatic light. So as the number of slits increases, fringes become narrower and brighter, and this is because there's more waves arriving exactly out of phase or exactly in phase, and this increases the destructive as well as constructive interference respectively. The intensity fringes still decrease either side of the central maximum because there's a single source of light that this is being modulated by. There is a good image of this on page 315 of your workbooks, and it just shows that the more slits you have, the more intense the maximas will be, but the width will be smaller, and that corresponds with more destructive interference occurring. So the width's narrowing corresponds with destructive interference. The more intense or the greater intensity of light corresponds with the increased constructive interference that occurs. You don't need to use these terms here. All you have to do is as long as you're able to sketch the graph of the intensity distribution, then that will be fine. This is just to demonstrate intensity relevant to slits. If you had to draw the intensity distribution, then this would look a bit like this, with the central maximum in the middle, and then the intensity slowly decreasing either side of the central maximum. Spectroscopy is a technique used for analysing wavelengths of light emitted by, excited SOSFAM atoms or molecules, and wavelengths of light appear as coloured spectral lines on a spectrum. A spectrometer, which is any instrument that probes a property of light, uses a diffraction grating to separate light into its spectrum. A spectroscope is an example of a spectrometer, and spectroscopes can be used to analyse light from stars, planets, discharge tubes, or chemical mixtures. This is an example here of what a spectroscope might look like, and this is a periodic table of spectra. So these are the spectral lines that each element emits, or the electrons of each element emit when they're going from their excited state back to their non-excited state. So we'll take a look at a spectroscope. This is focusing on describing how a grating can be used to experimentally determine the wavelength of light from a monochromatic source. These diagrams are like mirror images of each other. So in this one here, the light source will be going in through this way, and then obviously here the light source is going in through this way here. But it's helpful to have the bird's eye view and the side-on view. So light passes through a slit into a collimator, and then a lens at the end of the collimator focuses the light that's entering into parallel rays to then pass through a diffraction grating, which is here, or on this diagram it doesn't actually show, but I'll just draw one on. Light is then dispersed after passing through the diffraction grating into its spectrum, and it enters a telescope via a lens which focuses the light onto a screen, and that's for observation by an eyepiece. The angular position is measured via a scale on the table. So you'd have someone looking in through the eyepiece, and they'd be adjusting this telescope, or this side's telescope around the table, which would have like a big protractor on it, and you'd be able to measure exactly what angle you were sitting at and what angle that spectral line was at. Because you've been able to determine this angular position via your scale on the table, the wavelength of the spectral line can then be determined using our path difference formula. Now we're looking at the bottom success criteria here, so we're just jumping around in terms of the order, but we will cover them all. So properties of gratings that are useful in spectroscopy. So the fact that gratings produce sharp spectral lines allows for the measurement of the wavelength of a given spectral line. So because you can determine the angular position of a spectral line pretty precisely, you can therefore use that to determine the wavelength. The small slit separation of gratings produces a large angular spread, and this also increases the accuracy of your wavelength measurements. And lastly, it's not so much a property of gratings, but the fact that you can use the grating formula allows you to determine the wavelength of a spectral line. So all of these properties are useful in terms of determining the wavelength of spectral lines. So I'll do an example now. So a spectroscope with a diffraction grating with 600 lines per millimetre was used to analyse light emitted from a neon discharge tube. A line from the first order spectrum was selected for analysis, and its angular position from the central maximum was 22 degrees. Calculate the wavelength of the light of the spectral lines. So we can apply our knowledge of spectroscopy with our path difference equation as well as our diffraction grating equation. So we know that we're going to need to use our path difference formula. We know that we're looking for the wavelength. We know that theta is equal to 22 degrees. We know that m must be equal to 1 if we're just talking about the first order spectrum, and we know that d is equal to 1 on n, which is 1 millimetre divided by 600 lines, or for metres it will be 1 metre divided by 600 by 10 to the 3 lines. So that's how many lines there must be in a metre if there's 600 in a millimetre. So we can rewrite this. So lambda is going to be equal to d sine theta divided by m, and lambda is also going to be equal to 1 on n sine theta divided by m, which will be sine theta n m, or you could do d sine theta on m, which would be 1 on 600 by 10 to the 3 times by sine theta divided by m, which is 1. I'm just going to do it this way, that you can do it multiple ways. So this is going to be sine of 22 degrees over 600 by 10 to the 3, and then m is 1. So you'll end up with a wavelength of 6.2 by 10 to the negative 7 metres. So that's the wavelength of the light of the spectral line if the angular position is 22 degrees. So now I'm going to spend a few slides describing and explaining the white light pattern produced by a grating. So white light is a continuous distribution of wavelengths from 400 nanometers, which corresponds with violet light, and 700 nanometers, which corresponds with red light. So each value of m, if we're talking about white light that's been diffracted through a diffraction grating, corresponds with a continuous spectrum of light that is being diffracted. One of the properties of white light diffraction is the fact that violet light reinforces at a smaller angle or a smaller angular position than red light, and you need to be able to show this mathematically. So, for example, if distance between center points of slits is 1.67 meters, how can we show that violet light reinforces at a smaller angle than red? We'll just use our path difference formula as we have been. So I'm just going to write this out here. So V for violet, and I'm just going to rearrange from the get-go. So theta is going to be equal to inverse sine of m lambda on d. Hopefully you can see that I've just rearranged the path difference formula there. 1.67 micrometers is going to be equal to 1.67 by 10 to the negative 6 meters. We'll just use m equals 1, so the first maxima, to demonstrate this. So the angle for the angular position of violet light in the first maxima is going to be equal to inverse sine of 1 multiplied by the wavelength of violet light, which is 400 by 10 to the negative 9, divided by the distance between slits, which is 1.67 by 10 to the negative 6 meters. And then that will end up being 13.9 degrees. I'm just going to zoom in to do this for the red light because I'm running out of space. So for red light, theta is going to be equal to inverse sine of m, which is 1, and then 700 by 10 to the negative 9 meters, divided, which is the wavelength, divided by 1.67 by 10 to the negative 6. If you pop all of this in your calculator, you'll end up with an angle of 24.8 degrees. So 24.8 degrees is obviously much more than 13.9 degrees, so violet light is just going to have a smaller angular position than red light when white light diffracts. The next thing that we need to show is that the angular spread is greater at higher order spectrum, so when m is bigger than 1, so 2, the spectrum, or the second spectrum, is going to have a larger spread than the first spectrum. The third spectrum will have a bigger spread than the second spectrum. So we'll show this, that the higher order spectrums have larger spreads. We'll show this mathematically. To start off, we'll recall our first order angular spread. So I'm just going to use delta theta of the first spread, and that was 24.8, so the angular position of red light minus 13.9, which is the angular spread of violet light, and that is equal to 10.9. So the angular spread of the first order spectrum is 10.9 degrees. If we now have a look at violet light, we'll use almost the exact same equation. It will just be theta is equal to inverse sine of m equals 2 this time, and then 400 by 10 to the negative 9 divided by 1.67 by 10 to the negative 6. So that was the distance between slits, and this will result in an angular position of 28.6 degrees. Sorry about the wonky 8 there. Now if we do the same for red, the angular position of red is going to be at m equals 2, because we're looking at the second order spectrum now, and then 700 by 10 to the negative 9 meters for the wavelength of red light, divided by 1.67 times by 10 to the negative 6. Pop all of that in your calculator, you'll end up with an angular position of 57 degrees. And now for the final step, if we work out the angular spread of the second order spectrum, we'll be minusing 57 degrees. We'll be minusing 28.6 from 57 degrees, and that will bring us to 28.4 degrees. So the angular spread of the first order spectrum was only 10.9 degrees, whereas the angular spread of the second order spectrum was 28.4 degrees. So the amount that the second order spectrum is spread out is much larger than that of the first, and that is the same for each higher order. It's always larger than the previous one. And lastly, for the characteristics of white light, there's an overlap between the second order and third order spectra. We need to show this mathematically, again, if the distance between the centre points of slits in the diffraction gratings is 1.67 micrometers. So how we show this is that we calculate the reinforcement of the longest wavelength in the second order spectrum, and then calculate the reinforcement angle of the shortest wavelength in the third order spectrum. So for the second order spectrum, the longest wavelength is going to be red, because red is 700 nanometers, and we calculated before that the angle of reinforcement for red wavelength is 57 degrees. Now for the third order spectrum, we'll calculate the shortest wavelength. This will be very similar to the calculations that we've been doing already. So the angle of reinforcement for violet light in the third order spectrum is going to be inverse sine of 3, so m equals 3 for the third order spectrum, multiplied by 400 by 10 to the negative 9, and that is divided by 1.67 by 10 to the negative 6, so d, the distance between the slits. If you pop all of this into your calculator, you'll end up with a reinforcement angle of 45.9 degrees. And obviously 57 degrees is beyond 45.9 degrees. So the end of this second order spectrum, so where red light reinforces, is greater than the beginning of the third order spectrum where violet light reinforces. So there must be an overlap between the second and third order spectra. And finally, the last thing that we're going to look at is determining from the distance between slits in the grating the maximum number of orders possible for a given grating and wavelength. So, for the maximum number of spectral orders from a diffraction grating, we need to remember that it's impossible for theta, so the angular position, to be greater than 90, because otherwise light would be bending back on itself. So therefore, the maximum number of orders occurs when theta is equal to 90. And again, we use the path difference formula, but because sine of 90 equals 1, the formula simplifies to m equals d divided by lambda. This question, what is the maximum number of complete spectral orders for white light? Again, if d is 1.67 micrometers. So we'll use d sine theta equals m lambda, and of course this will simplify to m equals d divided by lambda. Because we're talking about white light and we're talking about the maximum number of complete spectral orders, we want to think about the longest wavelength in white light, because as we discovered in the previous question or the previous example, the spectral orders overlap. So we could, if we were to use the shortest wavelength, we'd determine how many times violet light reinforces. We're not determining how many times red light reinforces. So violet light could reinforce before red reinforces, and red might not reinforce by the time we get to theta equals 90 degrees. So we need to use the longest wavelength of white light to determine how many complete spectral orders we'll get. So d is going to be equal to 1.67 by 10 to the negative 6 meters, and the wavelength for red light is 700 by 10 to the negative 9 meters. Pop this into our equation and we'll get 1.67 by 10 to the negative 6 divided by 700 by 10 to the negative 9, and popping that into our calculator we'll end up with m is equal to 2.4. So therefore 2 complete spectral orders occur. So this is 2 spectral orders that are observed either side of this central max.